Okay, so we talk about decision tree. The problem is the question is how fast we can sort. So, this is the question. So far we have seen some comparison based sort. All the sorting algorithm we have seen are comparison based. So, that means we are comparing two elements and then we are taking the information by comparing the elements and we are taking some decision. So, those are comparison based sort. So, we have so far the sorting algorithm we have discussed are basically insertion sort, then we talk about merge sort, quick sort, and we have discussed a version of the quick sort which is randomized quick sort, and then we talk about heap sort, but all are basically comparison based sort. That means we are comparing the elements and we are taking some decision. We will discuss the decision tree. So, now what is the time complexity? Best case, average case and the worst case. So, for insertion sort, what is the best case? When the array is already sorted. So, then we are just comparing with the previous one. So, it is basically order of n, and the average case we discussed that on an average maybe we have to come from halfway. So, it is also giving us order of n square, and the worst case when the array is the reverse sorted, it is order of n square. And merge sort is all the cases it is n log n, because we do not really care whether this is sorted or reverse sorted. In the merge sort, what we are doing? We are going into the middle and we are sorting this part and we are sorting this part recursively. So, at the conquer phase, this is a divide and conquer approach. So, we do not really care how whether they are equal, whether they are sorted, reverse sorted. We are going to the middle, we are sorting this, we are sorting this recursively, that is it. So, that is why it is the recurrence is that. So, we got this solution for the merge sort. And what is the quick sort? Quick sort, the best case is when the partition is pivot is the good pivot. So, it is partitioning half n by 2 n by 2. So, then we got n log n. So, average case for quick sort, this will come under the randomized quick sort version, and the worst case is when it is, because our partition is first element we are choosing as a partition. So, if you take the input as a sorted or reverse sorted, then always partition will take the pivot as a minimum or maximum every time in the subsequent step. Even though if we choose the partition as other elements, say middle element of the array n by 2th element. So, we can always construct a input where we put in the middle element the minimum one. So, we put the, this is the array. So, for this array, this is n by 2, we put the minimum one here for this whole array. Again we come to this sub array, we put the minimum one among this here. So, one can easily construct a input where every time the pivot will be the minimum one. So, then our this partition will be a bad partition and it will partition is 0 is to n by 1. So, that is the worst case. So, that solution we know is n square. And now we, to overcome that problem, that we should not know which position we are choosing as a pivot. So, that one should not come with some input where our algorithm is performing badly. So, to overcome that problem, we choose the randomized version of the quick sort. That means, we choose the pivot randomly. So, we will not say that we are going to choose this element as a pivot. So, that will be decided at the runtime. So, that will be depend on the random number we are getting. So, for that the best case is again n log n, and the expected it is also n log n, because we the expected runtime of this, and the worst case is always n square, even for the randomized version of the quicksort, because we maybe it happened that every time our random number is so bad that it is choosing the minimum or maximum of that corresponding sub array. I mean, so it will always give this, and the heap sort, it is basically n log n Okay, so, but we know that we are interested in the worst case analysis, because that is the most essential analysis one can think about. So, this worst case we have n log n, the best one. So, the question is whether we can do something better than n log n or not. So, in the worst case, the question is, in the worst case, can you do better than n log n in the worst case? So, that is the question. So, to answer this question, we have to talk about the decision tree. The answer is no. We cannot do better than n log n while we are using the comparison based sort. That means, we are comparing two elements and we are taking the information by comparing two elements and we are taking some decision. So, for comparison based sort, answer is no. No, if we are using any comparison based sort. Comparison based sorting algorithm. Okay. So, so how we can justify this? We will take help of a decision tree. So, what is a decision tree? Okay, decision tree. We will take an example. Suppose we need to sort 3 elements A1, A2, A3. Okay. So, to sort 3 elements, what we will do? We compare first A1 and A2, and here we are assuming the elements are distinct. So, we compare A1 and A2. So, if we compare two elements, there are two possibilities, because we have taken the distinct element. So, there are two possibilities, either A1 is less than A2 or A1 is greater than A2. If A1 is less than A2, then we will take this path and we will do the subsequence comparison before we reach to a decision, and if A1 is greater than A2, we will take this path and we will do the subsequent comparison before we take the decision. So, here in this path again we compare A2 and A3. If we compare A2 and A3, again we have two ways to go. So, this way is basically A2 is less than A3 and this way A2 is greater than A3. Now, if we take this path, then we can reach to a decision, and that decision is 1, 2, 3. That means, A1 is less than A2, less than A3, because this is A1 is less than A2, here A2 is less than A3. So, by transitive property of less than, we can say A1 is less than A2, less than A3. Now, if we reach to this path, then we need to do another comparison between A1 and A3. Then again we have two paths, A1 is less than A3 and A1 is greater than A3. So, if we reach to this path, then we have a decision 1, 3, 2. That means, A1 is less than A3, less than A2. And if we reach to this path, we have a decision 3, 1, 2. That means, A3 is less than A1, less than A2, because this path is basically telling us A1 is less than A2 and A2 is greater than A3 and A1 is greater than A3. So, A3 must be the minimum than A2, because from here so that because A1 is A2, A1, A3, so A3, A1, A2 like this. So, here we will do A3 and A1 and A3. So, if we reach here we can take a decision 2 1 3 and here we will do the subsequence comparison. So, here we will reach a decision, this is basically 2 3 1 and here 3 2 1. So, this is the decision tree where each label is denoted by each label is denoted by I is to j and this is the path where if I is less than j, this is the path for the subsequent comparison, but this is the path we will follow if I is less than j and this is the path we follow if I is greater than j, and then we will do the subsequent comparison here, subsequent comparison here and we will reach to a decision. So, each node is like this I is to j, that means we are comparing A I and A j and finally, we are reaching to a decision. These are all leaf nodes. So, these leaf nodes are basically the decision. Okay. Now, we can take an example, suppose we have 9 4 6, 9 4 6. So, A1 is 9, A2 is 4 and A3 is 6. So, we compare A1 and A2. So, which path we should follow? If we compare A1 and A2, then A1 is greater than A2. So, we follow this path, 9 is greater than 4 and now here we come. So, here we compare A1 and A3. So, 9 is greater than 6. So, we will take this path and here we compare A2 and A3. So, A2 is 4, A3 is 6. So, A2 is less than, we follow this path. So, we reach to a decision that A2 must be less than A3 must be less than A1. So, A2 is what? A2 is 4 which is less than A3 which is 6 which is less than 9. So, this is the sorted one. So, we reach to a decision by following this path. So, leaf, all the leaves are the decision. So, for any input, if we have an input, we are following this path. Okay. So, now if we have say, if we have the example is, suppose we want to have this, this part. So, if we have say 9, not 9, if we have 4, then 3 and then 6. If we have this is our input, then which path we should follow? So, this is our A1, A1 is greater than A2. So, we must follow this path and then A1 is less than A3. So, we must follow this path. So, here the decision is A2 less than A1 less than A3. So, A2 is what? A2 is 3 less than 4 less than 5. So, this is the decision. So, this we are reaching very fast. So, depending on the input. So, if we take this path, it is faster. So, what is the time for this? If we have an input, what is the time? Time is the basically the path we are following, the length of that path. Okay. This is shorter length, but this is bigger length. So, we are talking about worst case. So, what will be the worst case time? Worst case time will be the maximum length of the path. So, maximum level of this tree, and that is called height of a tree. Maximum depth is called height. Na? So, worst case time is basically height of the tree. Okay. Now, if we look at any comparison based sort, quick sort, insertion sort, merge sort, anything, and if we execute that, that is basically following a path in a decision tree, because in any comparison based sort we are comparing two elements and then we are taking some decision. So, we are following any of this path for the further comparison and then finally, we are going to a decision, finally, we are going to a leaf level. So, any comparison sort based sort execution on the input is basically following a path in the decision tree, because there also we are comparing two element and we are taking some decision, and then after that we are further comparing. So, that is the path of a decision tree. So, the worst case of that comparison based sort is basically height of this tree. So, if you denote this height by h, then how we can calculate h? Now, what is the number of leaves? Number of leaves is basically these nodes. These nodes are basically permutation of this nodes. So, that is basically factorial n, because there are n nodes. So, this is factorial n. So, so if it is factorial n, then is there any relationship we can draw from with the n and this number of leaves? So, this is a binary tree. So, if it is a complete binary tree, then what will be the number of leaves? Number of leaves should be 2 to the power h. Okay. So, 2 to the power h must be greater than factorial n, because this is not a complete binary tree, because this is ending here. Okay, it is complete means it should go at the end. So, this is the relationship we have. Okay. So, now how we can get something from here? So, h is basically greater than equal to log factorial n. Now, factorial n can be approximate by n by e to the power n. This is the Stallings formula. Okay. So, if we use this approximation, then what we have? We have basically h is greater than equal to log of n by e to the power n base this. So, this we can take n log n minus n log e base 2. So, this is basically greater than equal to n log n. So, height is basically omega big omega log n. So, height is nothing but the worst case runtime for any comparison based sort, because that is the execution of the decision tree from the root to the leaf. If you take any input, then for any comparison based sort you have to take root to the leaf. This is the height. So, the worst case runtime for any comparison based sort is equal to height of the tree. Decision tree, which is basically omega n log n, sorry, omega n log n, this is n. So, this we have proved that we cannot do better than n log n in the worst case if we are using comparison based sort. So, then what is the solution if we want to have a linear time sorting algorithm? So, we cannot use comparison based sort. So, there we will be using what is called bucket sort. So, there we will not compare between two elements. What we will do? We will see the value of the element and we will put into the bucket. So, no comparison between the elements. If we have to compare between the element, we cannot do better than n log n in the worst case, but we want to do a linear time sorting algorithm. So, that is not a comparison based sort. So, those are called bucket sort. We will see the value of the element and we will throw into the bucket. Okay. In the bucket sort, what we are doing? So, this is not a comparison based sort. So, we have some, we are taking some bucket, say suppose the numbers are elements are coming from the interval 0 and 1, and we have some equal sub intervals. Suppose there are n sub intervals, b n minus 1. So, what we are doing in bucket sort? We are just checking a number and we are putting into that bucket, and then after storing in the bucket, we are now sorting individual bucket by the insertion sort. So, we will take an example. So, suppose our numbers are like this, say 0.78, 0.17, 0.39, 0.26, 0.72, 0.92, 0.21, 0.12, 0.23, then 0.68. Okay. So, all the numbers are between 0 and 1, and suppose we have buckets say starting from 0 to 0.1 like this. So, we have say B 0, this is basically 0.0 bucket like this, I mean. So, B 1 0.1 like this, B 2 0.2 like this. So, I mean 0 to 9. So, B 9. Okay. So, this is 0.6 bar. So, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and last one is 9th bucket. This is represented by 0.9. So, this will go to the 6th bucket. So, we have this bucket. So, we will put here 0.06, and then this will go to the 0.7th bucket. So, 0.78 like this. We are filling the bucket, we are checking the element and throwing into the bucket. So, 0.17 and then 39, 0.39, 0.26. So, it will be here 0.26, then again 0.72, 0.72, 0.92, 0.92, 0.21, 0.21, 0.12, 0.23 will be here. So, this is the bucket filling. Now, we have individual bucket, and this number we are going to sort by insertion sort. So, suppose in ith bucket Ni is the number element putting into the ith bucket. So, we are applying the insertion sort on this, and we get this 0.12, then 0.17. Then again we apply the insertion sort on this, we get so 0.21, 0.23, 0.26. Then there is only one element 0.39, only one element then we have we will apply insertion sort on this 0.78 like this, then 0.92 sorted. Okay. So, this is a typically bucket sort. We will see the element and we will throw into the bucket, and then we will sort this bucket using the insertion sort. Now, what is the time complexity of this? So, here in this case we have 0 to 9 bucket, but in general suppose we have n buckets. So, let us write the code for that. So, bucket sort on. So, what we do, n is equal to size of the array, the number of element, and then for this is the filling the bucket. What we are doing? We are inserting aj or sorry ai into the b of n of ai. Okay. So, we have b 0 up to b n bucket. So, then we have basically n buckets. So, this is the bucket filling, then individual bucket we need to sort using the insertion sort. For I is equal to 1 to n, there are n buckets. So, we sort the list what are the element in the bi ith bucket with insertion sort. insertion sort, and then we just print the bucket. We just concatenate this bucket, we just print this bucket B 0 B 1 like this, P n minus 1 if it is up to n minus 1, we are starting from 0. So, this is the typical bucket sort. Now, what is the time complexity for this? So, time complexity will depend on suppose n I is equal to number of element going to ith bucket, going to ith bucket. Okay, then the run time for this is T n is equal to, so order of n, this is for filling the bucket, and then individual bucket we are sorting. So, there are n I is the, so n I square, this is the time taken by the insertion sort. There are n I element in the ith bucket. So, time is n I square and there are n buckets. So, this is the time complexity for this bucket sort. Now, if you take the expectation of it, because n I we do not know how many numbers will be going to ith bucket. So, if you do the expected analysis of this, so this is basically theta of n plus summation of expectation of n I square, and this can be proved that this is also linear by some taking some indicator random variable. Suppose we assume this is 1 if the ith element, if A I is going to a, this is 1 if A j is going to ith bucket, 0 otherwise, then basically n I is basically summation of x I j, j is equal to 0 to or 1 to n. Okay. So, now by taking the square of this term and taking the expectation, we can show this is basically linear. So, this is theta of n. So, this is the bucket sort time complexity, it is a linear time algorithm.